Hello everyone. So in this video, I will give you a brief introduction to the strategies for patterning on non-conductive substrate. This is not going to be a video with a NanoFrazor demonstration, but more an explanation of some concepts that I hope will be helpful for you to understand a little bit more the problem of patterning on non-conductive substrates with the NanoFrazor and the solutions that you can adopt. So let's follow this presentation that I hope will help you understand a little bit more. So the default NanoFrazor patterning, as written here, relies on electrostatic actuation. So we apply a potential difference between the capacitive platform and the substrate. So this requires at least a semiconductor because our cantilever is made of silicon. But if we have a non-conductive sample, we have some problems because we cannot accumulate charges on this surface, so we cannot easily apply potential difference and we cannot bend the cantilever. Usually we encounter these problems when we deal with substrate that have that are made of non-conductive material, but also when we have quite thick layers up to several microns. Several microns of insulating materials on top of a conductive material. So for non-conductive substrates, then we have to use a different approach. And two general approaches are pulsed heating and the use of temperature map. And both of them use the T-Peter temperature that as a mean to actuate a deflection by heating of the cantilever. So in this case, what will cause this deflection is not this potential difference that is applying between here and here, but the heating that is caused by applying a potential difference over the resistor of the heater of the writer. So let's see a little bit more in details the first patterning mode, pulse heating. And here we also find a quick recap of the default patterning mode. So when we pattern with the NanoFrazor in the, let's say, default mode for conductive substrate, we have our layout with different pixels, different depths in this case, and we apply a force voltage with a force pulse that can also be chosen with the interface of our software, and we turn on the heater throughout all the write field. And we apply this force pulse only for the pixels that we want to write. And the force is going to have different values of voltage because it's electrostatic actuation, depending on whether we want to write deeper or not so deep. So what happens when we cannot apply this voltage because our substrate is an insulator? Well, we can try to use this pulsed heating mode. Basically, instead of having the heater always on throughout the write field, we only turn it on for the pixels that we want to write. In this case, one first limitation that we can see is that the grayscale is not really possible. We can only do 2D patterning because, as you can see here, we apply this heat pulse for a chosen temperature for all the pixels. So in this case, we will obtain a result that is two-dimensional because the temperature will be always the same. Usually, we tend to lower the forward height when patterning because of this thermal bending effect. So in general, we'll say the forward height is typically lower between 0 and 150 nanometers, but can be even higher, let's say up to maybe 250 nanometers, as we will see in the videos of this topic. And when we pattern with the default mode, usually we take a forward height that's between 250 and 350 nanometers because the write force bends the cantilever strongly or more effectively. So What are the settings that we can typically use? Well, we have some recommended settings that you can find in this slide, but in general, you can also try to play with this value even more and find ranges even different from this, and when you're more comfortable with your specific samples. So in general, what I will say is that most of the time, slightly higher temperatures are needed. So add 100°C to your usual temperature, and the usual range is quite large, as you can see from here. Goes from 700 to 1,350. More than 1,350, I will try to not use because it really pushes the temperature to values that are very close to the melting point of silicon, which the cantilever is made of. And one thing that you have to keep in mind is that the higher is the temperature, the larger is going to be this thermal bending effect. So the higher your forward height also will be. So you have to find a good balance between these two values. And also, as written here, the forward height is much lower than usual. We can start with 100 nanometers, but another approach that you can also use is maybe start with 250 nanometers and increase the temperature and see when you start writing because of thermal bending. In this case, we mentioned this heat pulse because we want to try to use a pulse heating setup. And from the software, you can choose a range for the heat pulse. Usual is between 15 and 50 microseconds, but you can increase it if you want to have a deeper patterning and longer pixel times. Of course, the heat pulse must be smaller than the pixel time because, as we can see here, we apply this heat pulse for every pixel. So in general, these are the settings that we can recommend you, or the ranges that we can recommend you, and you will see also more in detail from the videos that we can have a more general approach to this problem. And as also written here, you can set, for example, the force pulse time to 0 microseconds, because anyway, it will not really affect our patterning if we cannot apply a force pulse. So here in this slides, you can see a sort of recap of the main parameters that you should have a look at when trying to use a pulsed heating mode. Remember always to check this pulse heating. So if you want to use pulse heating, check here. If you want to use temperature map, check here. So otherwise it will not be applied. And yeah, the force in this case you can set to 0 because you will not be able to effectively use an electrostatic actuation. Another mode that we can use to pattern is through temperature maps. What are temperature maps? Well, let's see again a similar slide to the first one that we saw for pulse heating. We have our default mode and temperature map. So temperature map, we can apply a different temperature on the riser voltage for each pixel. So why is this interesting? Because first of all, this allows us to write also in grayscale on insulating substrates. In this case, we see that write force voltage, in case we're patterning on insulating substrates, it's 0 because we cannot apply any force. And in general, this different temperature will cause different bending of the cantilever. So the riser gets heated up according to an overlay temperature map, and this causes a different thermal induced bending of the cantilever. In general, the temperature map is a function that can also be applied with the right force voltage. So it's not true that you can only apply temperature map without force. Let's say if you want to for example, pattern on materials or explore some more exotic applications of the NanoFrazor, you can combine temperature map and force maps. But for the sake of this video, which is about insulating substrates, I mentioned that the right force voltage is not used. So in this case, we can see that the temperature map can be set on top of any sort of force map. Here in this image in gray, we have a force map, the default geometry that we import, and on top of this geometry we can place a temperature map, which has a grayscale modulation of the applied temperature, while the first one has a modulation of the applied force, which cannot be used on insulating substrate. And if you are more curious about temperature map functions in general, we also have a video in our playlist regarding just temperature map, which I recommend you to watch. So also this process of applying the temperature map, which is explained in this slide, is well mentioned and well explained in that video. Just to give you a quick recap, basically we have to import our base layout, our geometry as usual, choose our pixel sizes and all the parameters of the geometry here. Then the depth will not have any effects because we don't have any force, so again, it doesn't really affect your patterning. Then we add this as new layout, so we will add this force layout in the standard way that we use to import the geometry. Then we go to the optional tools in the temperature map here, and we choose the target field here, and we apply a temperature map. So we open the files and we select an image, a PNG or JPEG or any grayscale file source that we can apply on top of our geometry that's based on the force. And we can select any geometry to apply on top of, let's say, our Mona Lisa. It doesn't have to be the same geometry necessarily. This is also one important thing to mention. Then we create, or we can also create from target field. And in this case, if we have a Mona Lisa and we want to create the same, we press create target field. Then we add this to the target field, and in the session CLL patterning parameters, we check the temperature map. So as also written here, it is possible to load different layouts to the temperature maps. And again, for more information, I would recommend you to watch the suggested video. So again, for temperature map, we have some recommended settings. Usually we have quite a wide range of temperature that we can use. The advantage of the temperature map is that we can set a minimum and a maximum temperature of the heater. So we can write in grayscale, but this mode doesn't have any feedback. So at the moment, the NanoFrazor does not have a feedback based on temperature. So we will have to try to pattern one field with the settings, see how it looks like, and then adjust them accordingly. In this case, we also try to use a forward height that's lower than usual, and the pixel time can be adjusted between 25 and 100 microseconds. I will say usually the starting values can work well, but if you are comfortable with playing with these values and you want to explore more options, this is another parameter that you can adjust. So what's the typical approach? Let's say we import this temperature map with this specific minimum and maximum temperature, and this is the result that we get. And we see that the patterning is deeper both on the bottom part and the top part than the target. So that means that the lowest temperature is too high and the highest temperature is also too high. So this means that we have to reduce both of them for the next field. In this case, we basically are the living feedback of the NanoFrazor. So it requires a little bit of experience and mastery of in general the effect of temperature over patterning and the thermal bending, but with some few exercises and few tests, you should be able to have a good handling over this problem. This is the general approach. So this is the last video, the last slide of this video. And in the next videos of this topic, we will see practically how to pattern on insulating substrate, the strategies that we can adopt, both temperature maps and pulse heating. I hope it was helpful, and good luck with your research.